Hello everyone, I'm Ishaq ZOUAGHI and I'm here to present our paper entitled Query Optimization for Large-Scale Clustered RDF Data. Let's start giving some context to our work. The flexibility offered by the Resource Description Framework lets it become the most widely accepted standard to model the linked data from the web. It has been useful especially to gather more than 1,400 datasets from many disciplines in the linked open data. Some of these datasets, like Wikipedia, collecting structured information from Wikipedia, has more than 170 million triples. In other domains like genetic and biology, the BELLATRECHE RDF dataset counts now more than 11 billion triples. To query and manipulate this dataset, languages and protocols have been introduced. Among them, Sparkle, which is the standard declarative query language proposed by the World Wide Web Consortium. With the fast growth of large-scale RDF dataset, efficient processing of Sparkle has become a very challenging task. So, it's necessary to have systems that guarantee the good performance to store, manage, and query RDF datasets. We find among RDF processing systems two main approaches. The one built on top of existing systems, named non-native, and the other system built specifically for RDF, named native systems. I will give a brief overview for both strategies. Let's start with the non-native approaches. Most of its systems are built on top of relational database. The RDF triples are stored in table, and queries expressed as Sparkle are translated into SQL. Among the systems following this approach, we have RDF3X and Virtuoso. But the drawback of this approach include the loss of the graph structure in the storage layer, the increase of the complexity for queries with many triple patterns, and mostly by the wrong estimation caused by ignoring the correlation between triples. Additionally, for complex queries with several joins, these systems have major limitations. To overview this drawback, we find many native approaches. Among them, we have the graph-based systems, representing RDF as a graph and whose query execution is performed as a graph exploration task. Experimental results comparing these systems show that graph-based system GStore performed quite better when solving complex queries, but as seen in the table, failed to scale to a graph with more than 100 million triples, since the system works mainly in main memory. On the contrary, relational-based systems scaled well, but did not support the entire spectrum of Sparkle queries, and had bad performance for complex queries. Scalable system combining the graph exploration process and the data fragmentation was presented in this work. As shown in this experiment, the system processes successfully all the tested datasets. Our work is focused on finding optimization strategies for this kind of systems, based on graph exploration and partitioned graphs. Let's now see an example of the graph exploration process and how it can be affected by different execution strategies. Consider this Sparkle query and its graph from the Yago dataset. Note that we have many ways to explore query. For this query, we have 40 different plans. For example, in the first one, we start from P, and we move forward to find the matches. Then we move to the node city, and advance backwardly. Each one of these strategies has a cost expressed in terms of execution time. After executing query plans in 41 GB dataset, the execution time of the first plan is less than 1 second. However, executing the 40th plan takes more than 5 minutes. Now, which of these strategies is better? How to decide which is the optimal query plan? How can we model the exploration process knowing that the best plan finding algorithm is NP-hard? The proof is given in the appendix of our paper. Our contributions give solution to these challenges. We start modeling the query execution of graph-based systems. Then we present a cost model according to the disk and the network costs based on statistics. And finally, we propose an algorithm to choose the best execution plan. This is the outline of my presentation. I will briefly describe the related work, then I will detail our approach divided into the query execution model, the cost model, and the best plan finding algorithm. Then I will present our experiments. Finally, I will present our conclusion and describe our ongoing works. Our related work discussed two of the main optimization strategies used in RDF systems. The first one, data organization and partitioning, which influence the performance of an RDF system before the query execution. We describe the partitioning strategies used in the literature briefly. We divide the strategies in 4 groups. The naive solution stores the data in single triple table. To optimize this approach, the data could be indexed, as is the case in RDF3X. Other approaches store the data in single table per predicate. Others group the data by subject. And finally, the approach like emergent schema and eager try to find the schema implicitly expressed in the data. The other optimization strategy related to our work occurred during the query execution and deal with the joins order. To this end, many approaches have been proposed. The first one collected the statistic from individual predicates, or by predicate pairs. Other approaches, more sophisticated, used the concept of characteristic sets. Finally, the approach published in the EDBT 2016 proposed some heuristics to decide the best join order. There is many problems with these strategies. First, they assume the independence between attributes. Second, they are unable to consider all combination of patterns. And they produce big estimation error for complex queries. Our solution proposed to partition the graph finding an implicit schema as it was proposed in the literature. We present a novel execution model and a cost model based on statistics that we collect for each implicit entry that we call graph fragment. Finally, we propose an algorithm to find the best execution plan. Let's start with the data storage model. For this, I will first define two background concepts used to describe the proposed partitioning strategy. Let's recall that an RDF triple is formed by a subject, predicate, and an object. Let's begin with the data star concept. We named forward data star set of triples sharing the same subject. The subject is said to be the head of the data star. A backward data star, on the contrary, groups the triples sharing the same object, and the head of the data star is the object. Next, I will give the concept of the characteristic set. The characteristic set is set of predicate in data star. Set of predicate of forward data star is named forward characteristic set. Similarly, the set of predicate of backward data star is named backward characteristic set. A graph fragment group data star sharing the same characteristic set. There exists as well forward and backward graph fragments. Let's see this better with an example. We will use this graph showing information related to the air traffic control in the rest of our presentation. As mentioned before, the data are first grouped in forward and backward data stars, then the data stars are grouped based on their characteristic sets. For example, after the fragmentation of this graph, we get 3 forward and 5 backward graph fragments. The graph fragment 1 group 2 forward data stars, sharing the same characteristic set composed of the predicate label has flight. The graph fragment 6 group 2 backward data stars, sharing the same characteristic set composed of the predicate label arrival. Let's now give some concept of the query execution model to describe the partitioning applied into a query. Forward query stars groups node named the head and its outgoing edges. Backward star queries groups node named also the heads and its incoming edges. Let's consider the following query. We can partition it into 3 forward query stars and 3 backward query stars. This forward query stars has as a head the variable node C. This backward query stars has as a head the variable node M. The exploration process of query expressed as an ordered list of forward and backward query stars. As we see here, for this query we have 8 acceptable plans. Now, what's an acceptable plan? First, an acceptable plan must cover the whole query graph. This is quite straightforward. For example, this plan is not acceptable because this part of the graph is not covered. The second condition is that the head of query star other than the first one must be instantiated. We can see an example starting from the variable node C. We explore forwardly from this node, as indicated in the plan. However, exploring from the backward node M is impossible, since its head is not yet instantiated. We put these conditions for 2 reasons. First, because considering only acceptable plans reduces considerably the number of possible plans to calculate the cost. Secondly, we know that plan not validating the second condition will be much more costly, because they induce full scan of fragment and then Cartesian product to find the mapping. Now, among this acceptable plan, how to choose the optimal one? Now we will discuss the cost model that we use to choose an optimal query plan. Let's first discuss the statistical needed to calculate the cost of each plan. We consider an RDF graph partitioned using the model that we presented before in forward and backward graph fragments. The fragments are distributed to the worker nodes in case of distributed system, and for each segment we calculate the following statistics. First, the distinct represent for forward fragment the number of distinct subjects in the fragment. For backward fragment, it's the number of distinct objects. Second, the count represents the number of edges with the predicate E in the fragment K. For example, we suppose that there are 2 edges in the fragment 3 with the predicate 5 as a label. Third, the distinct node edge is quite similar to the count presented previously, but it's count only once for each subject or object, the number of outgoing or incoming edges with predicate P. Finally, the selectivity factor measures the proportion of the number of nodes in the fragment K pointing to another fragment G with respect to predicate E. Its value is -1 if the fragments are not related with predicate, but because they share the same subject or object. Let us discuss the cost model. For each query plan, we calculate the disk and network cost. As seen in the previous slide, each query is decomposed in query stars. The total cost is the sum of costs for each query star of the plan. The disk cost estimates the number of disk pages manipulated by the query. For this, a candidate set of fragments is obtained using the characteristic set of each query star. For the network cost, using the selectivity factor, we estimate the number of intermediate results sent from one worker to another, considering the actual location of the fragment in the cluster. Now, we present the optimal plan finding algorithm. Using the cost model presented before, we use a branch and bound algorithm to choose an optimal query plan without enumerating all the possible acceptable plans. To discuss this algorithm, we will introduce 2 main concepts: the allowed stars and the distance among query stars. For a given subquery plan, the allowed stars set is a set of star queries that could be joined to a plan to form an acceptable plan. The distance between 2 star queries is the number of edges between their heads. For example, the distance between the forward query stars in C and the backward query stars in M is 2. Let's do a run of the algorithm. We start from any query star. We initialize the plan as an empty set of query stars and also initialize the cost to be infinite. Let's suppose that we start by the forward query star C. We calculate the cost of executing only this query star with the previous cost model. In this case, the cost is C1. Since this cost is smaller than the initial cost, and query is not a complete acceptable plan yet, we enumerate its child branch using the list of allowed stars. Then, for the plan formed by forward C and forward F, since the allowed star is empty, the plan is complete. We observe that its cost is smaller than initial cost, initialized to infinite. Then we update this plan as the best plan and update the global cost. Since the previous node with cost C1 still has more children, we continue exploring. In this case, forward C and backward Alprat have total cost bigger than our best plan cost, which is C2, so we don't go further with the exploration. If we find an acceptable plan in another branch with a smaller cost than the one found previously, we update the best plan, and so on and so forth. Let's now describe the experimental study used to validate the feasibility of the statistical generation model and the ability of our cost model and the optimal plan finding algorithm to choose the optimal query plan in graph-based system. But first, I will present our experimental setup. We performed all our tests in single node running Ubuntu server with 1 TB of hard disk and 32 GB of RAM. We tested our approach in graph-based system, supporting the fragmentation model that we presented before. The chosen system was the one called Combining Fragmentation and Graph Exploration, presented in this paper. The statistical model was implemented as a Python script, running right after loading the data to the previous mentioned system. Our cost model and the optimal plan finding algorithm was developed in Java, and we used 2 synthetic and 2 real datasets to validate our approach. Specifically, WADIV and LUBM as synthetic dataset, Yago and DBLP as a real dataset. We divided our evaluation in 3 phases. In the first one, we evaluated if the statistics collected from the dataset had a reasonable size and a reasonable calculation time. So we found that the size of the statistics file is insignificant compared to the total size of the dataset. And for all the real dataset, the collection process was equivalent to less than 10% of the loading time. For synthetic dataset, LUBM had similar performance, but for WADIV, the number of different graph fragments was very big, slowing down the calculation of selectivity factors. In the second phase, we will show the result evaluating the estimation calculated with these statistics. For this, we used the relative error to compare the estimation of disk and network cost versus the real values. We used the execution logs provided by the systems mentioned before. For each dataset, we evaluated at least 10 queries, but for the sake of the presentation, we choose to show the most representative queries with the different shapes, either linear, stars, or more complex ones. To evaluate the estimation used for the disk cost, we compare the number of estimated read subjects for forward fragment and read object for backward fragment versus the real number of subject and object read. For the network cost, we compare the estimated intermediate result sent between workers with the real ones that we get through the logs. For most of the queries, the estimation were not that far from the real values. However, as we will see next, even for values which the estimation is not the most accurate, they didn't affect the choice of the optimal plan. In this phase, we evaluate the choice made by the optimal plan finding algorithm. We use the precision measure presented here to evaluate, based on the number of acceptable plans, ordered by cost, and which of them we have chosen. For all datasets, we choose almost always the best plan, or at least plan from the top 3 acceptable plans. For LUBM, we always choose the best plan. Let's now summarize our work. First, we provided a logical structure modeling the execution of graph-based systems. For this, we provided partitioning schema as it's done in the relational model, but fragmenting the graph in forward and backward fragments. Then the query is also partitioned following the same structure, and the execution is better tracked. Second, we provided a novel cost model comparing equivalent logical execution plans based on statistics. We described the statistics collected and showed that their generation and storage are suitable process. Furthermore, we studied formally the complexity of the problem related to the choice of the best execution plan, and we proposed branch and bound-like algorithm, allowing to find the best plan for a specific query. Finally, we used synthetic and real dataset to validate our approach. Our results showed that the cardinality estimation based on our model are very precise, even if the collection of statistic size is negligible. In the future work, we plan to explore other optimization strategies applying during the query execution based on the collected statistics. This technique would allow to avoid sending the intermediate result to a fragment that, according to the statistics, don't have much change to the query. So, is this optimization effective? How to build it? How to update the statistics in dynamic workload? And what's the influence of the data structure used to store the triples? That was my presentation. Thank you so much for your attention.